Hello, good morning, viewers. Today I am going to explain some simple questions based on spectrometry. The purpose of this video is to teach you, to let you know how do we write question answers in a precise and correct manner, in a very brief manner. So for that purpose, I have selected few questions taken from two chapters, vibrational spectrometry and photon magnetic resonance spectrometry. With these four examples, I will just try to explain how can we precisely and correctly write answers of questions. The first question reads like this. How can you distinguish between an aldehyde RCHO and a ketone RCOR from their infrared vibrational spectra and also from their H1NMR spectra? You see, both aldehydes and ketones in their IR spectra. So, the carbonyl stretching peaks at about 1730 reciprocal centimeters. But the aldehydes also show a small peak for the aldehydic CH bond. This peak appears between 2780 to 2800 reciprocal centimeter. Although this peak is very weak, but it can be identified because it appears in a region where no other peaks appear. So aldehydes and ketones have one similarity. Both have carbonyl group and their carbonyl group stretching is absorbs as a very strong peak where at about 1730 reciprocal centimeter. But aldehydes have also a CH peak which can distinguish them from ketones. Here I must tell you one more thing. The carbonyl stretching of aldehydes is at about 1730 reciprocal centimeter. For ketones also, it is in the same region, a bit lower because carbonyl group of ketone is somewhat less polar than the aldehyde group because carbonyl group in ketone is beset by 2 plus IR groups. When we come to BMR spectrum, the aldehydic CH resonance signal appears at about 9 to 10 ppm, while the CH very near to the carbonyl group absorbs at about 2.1 ppm. Aldehydes show the aldehydic H signal at 10 to 9 ppm. Ketones do not show this signal. Therefore, IR H1NMR spectrum of aldehydes and ketones can readily be distinguished. Here I have drawn the diagrams. You see, the upper diagram shows two peaks. One for aldehydic CH at about 2800 reciprocal centimeter, and the other peak is large one, very strong peak. It is for the carbonyl stretching peak. Below are ketones, only the carbonyl peak is there, no CH peak. Thus, IR spectroscopy can be very easily used to distinguish between aldehydes and ketones. Aldehydes show CH peak also, but ketones do not show this peak. Here, the aldehydic CH absorption in PMR is between 10 to 9 delta. Ketones do not have any such peak. The second question reads like this. How can IR spectroscopy be used to distinguish between RNH2 primary amines, RNHR prime secondary amine, and RRR and tertiary amine? The answer to this question is written very legibly here. The primary amino group NH2 shows two NH stretching absorption peaks at about 3350 centimeter inverse anti-symmetric NH stretching another peak at about 3300 reciprocal centimeter, symmetric NH stretching, both as strong broad bands. Secondary amino group contains a single NH bond, therefore it shows only one peak in this region. Remember, primary amino group have two NH bonds, so they show two peaks, one for symmetric stretching, means both bonds elongating simultaneously, and one bond elongating, one constricting, that is called antisymmetric. So primary amino groups show two peaks, one for antisymmetric stretch and another one for symmetric stretch. Secondary amino compounds, they contain a single NH bond, so only one peak appears. Tertiary amino compounds do not have any hydrogen on the nitrogen atom, therefore they do not show peak in this region. It means IR spectroscopy can be very safely used to distinguish between primary amino compound, secondary amino compound, and tertiary amino compound. Here one very important difference I must tell you. Compounds containing triple bond CH also show peak in this region due to CH stretch. But the difference from the amino peak is this, whereas amino peaks are strong peaks because NH bond is polar, the triple bond CH stretching peak is very weak because it is non-polar. So region is the same, both absorb near about 3300 reciprocal centimeter, but the styrenic compound absorbs as a weak peak, whereas the amino compound absorbs as a strong peak. One more difference can be quoted. If there is carbon triple bond carbon, then a weak peak should also appear around 2100 reciprocal centimeter. So on this basis, and acetylenic compounds can be differentiated from amino compound. Here see, a primary amino group shows two peaks. One is for anti-symmetric stretching, the other one is for symmetric stretching. The difference between the two peaks is about 50 reciprocal centimeter. The secondary amino compound shows a single peak in this region. On this basis, you can distinguish between primary amino compound, secondary amino compound, and tertiary amino compound, as I told earlier, do not have any peak in this region. Another question I read for you. PMR spectrum of a compound shows two absorption peaks, A and B, which are respectively at nu A 300 Hz and nu B 450 Hz, removed from the TMS absorption towards left side at 90 megahertz operating frequency of the NMR spectrometer. You have to calculate their delta ppm values, and you have also to calculate the frequencies nu A and nu B, and the operating frequency of the machine is 900 megahertz. Here I introduce you. When NMR data are reported in the form of frequency, such data are field dependent, but by a mathematical trick, such data are converted to field independent values called delta values. So remember very clearly, the chemical shift values reported in the form of delta ppm, they are field independent. But if they are reported in the form of frequency of resonance absorption, certainly they are field dependent. Sometimes this confusion arises. So be clear about it. Here I have given the formula for the calculation of delta value. Frequency for the sample peak minus frequency for the TMS peak. TMS is used as reference, divided by frequency of the machine, that is operating frequency, this whole multiplied by 10 to the power 6, then again read as ppm. I am going to tell you why this 10 to the power 6 is taken, why ppm is added there. So when you solve V sample minus V TMS upon V0, then we get a number which is 4 to 5 places removed from the decimal point. For example, the data could be like this: 0.000001 or 0.00025. So it is very tricky to remember such data. In order to remove the difficulty in remembering the data, we multiply it by 10 to the power 6. It becomes like this: 3.2, 1.4, 2.8, like that. Small numbers. We can remember such numbers as reference data. And then how to remove the inaccuracy introduced by multiplying with the factor 10 to the power 6. This inaccuracy can be removed by saying ppm, part per million. ppm means whatever you are speaking, that has to be multiplied by 10 to the power minus 6. Earlier we multiplied it by 10 to the power 6. Now we say ppm. So both these things cancel out each other. So inaccuracy has been removed, deleted. I repeat this point for you. If NMR data are reported in the form of frequency, they are very much field dependent. But the practice is to convert these data into universal data so that in whatever machine the data is recorded, delta ppm value comes the same. It is calculated using this formula. Delta is equal to frequency for the sample peak minus frequency for the TMS peak divided by operating frequency of the machine in the megahertz converted to hertz. Then this whole is multiplied by the exponential factor 10 to the power 6. Now we have introduced one inaccuracy because we have multiplied it by 10 to the power 6. So to get rid of this inaccuracy, we say ppm. ppm means multiply by 10 to the power minus 6. Now here I have shown the calculation. Delta A means delta value for the peak at frequency 300 Hz. It is calculated to be 3.33 ppm. The other peak, delta B, can be calculated similarly, and the result is 5 ppm. Again remember, ppm means 5 into 10 to the power minus 6 or 3.33 into 10 to the power minus 6. When the machine frequency is changed from 90 megahertz to 900 megahertz, you see the frequency values change accordingly. Now the new A becomes 3000, earlier it was 300. And similarly, new B becomes 4500 hertz, earlier it was 450 hertz. See very clearly this diagram shows when the machine operating frequency is 900 megahertz, the peaks are expanded, more separated than when it was 90 megahertz. So these are field dependent values. But the above formula converts these values to field independent values at whatever spectrometer frequency you are recording NMR data. Delta ppm values won't change, they remain the same, so that they are called universal. Now I am going to read you question number 4. Indicate the number of PMR peaks in sequence of their chemical shift values are 1, 3, 4, 4 tetrachloro 2-butanone. The compound name is 1, 3, 4, 4 tetrachloro 2-butanone. The structure of the compound is shown here. You can see there are hydrogen atoms in 3 different chemical environments. CH2Cl, 2 hydrogen atoms in the same chemical environment. CHCl, 1 hydrogen atom in a different chemical environment. Cl2CH, one hydrogen atom in a different chemical environment. Again, you see, these where there are two Cl atoms, those hydrogens are more de-shielded than where there is only one Cl atom. So clearly, this compound should show three different NMR signals. One for CH2Cl, one for CHCl, one for Cl2CH. And the signals for Cl2CH and CHCl will be found split into doublets because the two hydrogen atoms are separated by three single bonds only. Such hydrogen atoms split each other's signal. The CH2Cl part is far removed from other protons, so it appears as a unsplit signal called singlet. You see, Cl2CH is a doublet, CHCl is also a doublet, whereas CH2Cl is unsplit or singlet. The delta values appear in the same order, which is shown below. The CH2Cl appears somewhere around 2 ppm. CHCl is close to CO. It appears at a bit higher delta value. And most de-shielded proton Cl2CH appears even farther. More the delta value means more the de-shielding. Three signals, two split, one unsplit. Order of delta value is shown here above. The more the de-shielding, more the chemical shift value. The downfield side indicates de-shielding, but the upfield side indicates shielding. The delta scale is dimensionless and universal, independent of magnetic field, but the frequency scale, which is in Hertz, is field dependent. Protons separated by more than three single bonds do not split each other's signal. The spectrum is drawn like this. Two doublets, the structure is shown above the spectrum, and one singlet. Thank you.